And then likewise from here to here. Okay. These are your tau max. And then the shear, these are all your tau max. Okay. So now you understand what this data is, how it's measured. Okay, how it's measured is important, and from what is measured, what data has been shown. So all this data over here, you can see are all your principal stresses. Okay, now let's look at an example. Okay, let's look at a true real life example on how a structure is actually loaded. Okay, so again, you will have this example on Avenue to learn. You don't need to copy, it's available on Avenue. Okay, let's look at an example. Okay, so this is our introduction example. Okay, so at the end of the day, at the end of the day, what is this cost outcome? Okay, and I want you to observe this. Okay, I want you all to observe this example. I think by looking at this example is a key. Okay, to 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 study, or what topics to focus on, or the key on how to integrate different topics. Okay, so you can see the internal loadings at a critical section along a steel shaft of a ship are calculated to be a torque of 2,300 pound-feet. Okay, so you have a torque over here, and then you have a bending moment of 1,500 pound-feet. Okay, and an axial load of 2,500 pounds. Okay, so we are given that the yield strength. Okay, so you can see this is really interesting. We are given that the yield, right, is equal to positive 100 times 10 to the power 3 psi. Okay, and we are also given, right, that the shear in yield is equal to 50 times 10 to the power 3 psi. Okay, so these two are given. So what it asks us to do is determine the required diameter of the shaft. Okay, so these two properties are from material handbook, like the table I showed you before. Okay, material handbook. And if you were to look at how they acquire these material properties, they are what? Unidirectional. Right? For this case, the tests are due in tensile only, or sorry, I won't call it tensile, or tension only. The one below is shear only. Okay, so they only do the test in one direction. It's either in tension or in shear, like how I've shown you. Okay, so I'm going to copy this table over here. I'm going to copy this table over here, and then I'm going to paste. So the tests are either done in tension, okay, or in shear. So I'm going to get rid of this, on shear test. That's how from the test they got the what? That's how from the test they got this is 100 KSI, and over here this is where you get your 50 KSI. Okay, you can see that. Okay, now I'm going to put our structure now side by side. Question for you: is our structure loaded in compression only? Oh, sorry. Is our structure loaded in tension only? Anyone? Anyone? Or you guys are falling asleep now?
No, it is not.
No, right? It's not loaded in tensile configuration only. It's not loaded in compression configuration only. It's also not loaded in shear only. It is loaded in multi-directional. So it can be tensile shear, compression shear, right? Katie, right? You are right. It's no. So now, how can we analyze this structure over here, right? To use the data over here, which is loaded differently. One is unidirectional, the other one is not. Okay. Now the dilemma is this: how are we going to select the right material for this? Now, this is not a trivial matter. Okay, why I say this is not a trivial matter? It will take me 10 weeks to teach you how to select the diameter. Okay, at the end of the day, okay, you will have the confidence to select the right material or the right diameter based on the properties that you get from material handbook, and it is not unidirectional. It's going to be compound loading. Okay, it's going to be compound loading. Okay, so I'm now going to show you the procedure of doing. But before I show you, I show you the procedure, okay, I would like to, if I can, find it. Okay, now this is a term test question. Okay, and these are the sort of question that you have to solve at term test 2. Okay, some of you is like, oh, we are going to die. Okay, look, okay, this is a sort of structure that you will be getting. Okay, and you have to determine the stresses in either element A, B, or what? C. Okay, no idea with Mo circle. Hang Pao, don't worry. Okay, you will have the idea. You just need. I think during the term time is very stressful. Now I think it's the best time to learn this topic. Okay, so at the end of the day, this is a true structure. This is how it's loaded. Okay, from forces you're going to translate to stresses. Okay, as I said, this is term test 2. So term test 2 is 10 weeks away. I told you guys, right? It will take me 10 weeks to teach you how to draw the stresses on an element. And we have not done Mohs circle yet. Okay, we have not done Mohs circle yet. Okay, now let me highlight the procedure on how to solve this. Okay, now when I was an undergrad, I did not know. Even when I finished my undergrad, I did not truly know how to design a structure at all. Okay, it's sad. Okay, it's only when I'm doing my graduate school, when I was working in Rolls Royce, then I realized like, hey, what I've been taught in school is not enough. What do I mean by not enough? In 2P04, you guys are taught axial loading. You guys are taught bending moment very well. Shear force diagram, bending moment diagrams. Okay, this course is about integrating those uh, those specific field in normal stress and shearing stress to able to size materials, and the material behavior is carried out in just what? One direction. Okay. To choose the right material, the loading condition or something has to be normalized. Normalized means it does not matter on how the stresses are applied. Somehow we have to deal with it. Okay. Now, let's see how we are going to size this up. Okay. So let's look at this problem now. Okay. Okay. So this is the structure that we are looking at. Okay. So in general, I will show you the procedure that is usually taken, and then later you will, when we do more problems, you will understand the procedure better. So the first thing we do is we draw our transformation. Okay. So this is our using your right hand rule. This is X, this is Y. When that's the case, this is your Z direction. Okay. We know that. And then we know that over here. Okay. So before I go on, okay, at this moment, we are going to assume that failure will occur on this face and at this location, at this location. So this is where failure region will occur. Okay, at this phase. Okay, that is at the macro. Okay, MACROUG, macro analysis. Okay, we know that cross section is the most critical. Okay, so we have, I'm going to call this PX is equal to 2,500 pounds. Okay, so the PX, okay, so before we go on, we have to determine where is the centroid. Okay, so I'm going to sketch the centroid. Okay, so this is the centroid. So the 2,500 over here, this is what we call axial loading. Okay, that's axial loading. Okay, before I carry on anymore, we go for a short 5 minutes break. Okay, come back. I will start again at 8:05. Okay, so go for a short break, freshen up yourself, and then come back again. Okay, in 5 minutes time.